Greetings from Istanbul Technical University. I am Yunus Emre, the team leader of ITU Rover Team. We passed on our experiences from our participations in the University Rover Challenge for 4 competitions for this year's Rover, and now I present you the 5th generation Rover.
For overcoming any types of obstacle and adapting to rough terrain, a record suspension mechanism with a differential bar is used in the present Rover as in the last years. The height of the Rover from the surface is 0.3 meters, including wheels. The width is 1 meter and the length is 1.1 meter. The brand new wheels are manufactured from TPU and PETG by 3D printing to lighten the Rover and improve the field performance. The motors are positioned in the wheel's aluminum hubs like last year. This year, attention is paid to modularity and repeatability. The chassis of the Rover are produced from T-slot aluminum profiles, so assembly of the Rover much easier than last year.
The Rover can be controlled with both FRC Robotic controllers and STM32 MCUs. Magnetic absolute encoders are directly connected to the motor drivers with high power output and provide velocity data for close-up PID control. Electronic components are stationed in a separated box for modularity. Furthermore, we are developing a custom motor driver circuit and the power distribution board.
The kinetic distribution of the robot operating system is selected as the main framework for algorithm development. The main computer is communicating with the electronics using serial communication. Connection to the rover is established using Secure Shell protocol over 2.4 GHz frequency bands with ubiquity M2 HP RF module and 11 dBi high-gain omnidirectional antennas. Considering possible communication interruptions, a LoRa module operating in the 900 MHz frequency bands is used as a backup plan.
According to high precision and torque requirements, a linear actuator or a cycloidal gearbox is used for each of the 6 axes in the robotic arm. Structural parts of the robotic arm are manufactured from aluminum and stainless steel. Besides, cycloidal gears are manufactured from castamite. The end effector manufactured from PLA has 2 fingers that move parallel to each other and the fixed hook to lift up the 5 kg payload. Apart from axes in which linear actuators are used, brushed DC motors that have worm gearboxes in original power, other axes and end effector.
We control our robotic arms axis with the same model high-power motor drivers on the drive system. Thanks to the position data of the axis gathered from the absolute encoders, position-controlled PID drive is achieved for better implementation of the inverse kinematic algorithms. Communication is maintained by the CAN bus protocol. Its two-wide design provides efficient cabling and convenient placement of the electronic components are possible.
Our inverse kinematics algorithms are developed for manipulating various tasks with great precision. In this way, our gripper maintains transition on a smooth trajectory and provides better assistance to the operator. As a backup plan, move it and forward kinematics was prepared for sudden situations. Each method is tested one by one in the both real world and in the simulation environment. As a result of the mode switch algorithm, which is integrated into the main controller, swapping between forward and inverse kinematics algorithms is achievable.
The state machine model is chosen and integrated into autonomous navigation system to switch between nodes. Artificial potential fields and map-based SAR algorithms are being implemented to navigate effectively through the goal point while avoiding obstacles. MoveBase is also configured as the backup plan for the path planning algorithms. Open source Alvar ROS package is used for AR tag detection and localization. The user interface that developed last year is improved for more accessibility for the operator.
Unlike last year's vacuum design, 3 diggers are used for surface sampling in the present science laboratory of the rover. The system is manufactured from PLA and aluminum. All of the samples are collected separately by diggers, can be transferred to different test pods or Fourier transform infrared spectroscopy without contamination.
After the samples are taken, shift reagent is produced to determine aldehyde group molecules, and Bradford reagent is optimized to detect peptide bonds. Life investigation and habitability detection analysis results coming from ITU Rover Science Laboratory are supported by atmospheric gas sensors.
In our laboratory, microfluidic system is designed to detect bacterial communication molecules, and biosensors integrated to Rover to determine the likeness.
First of all, every soil sample's wavelength of the minerals is measured by Fourier transform infrared spectroscopy. In addition, 532 nanometer monochromator light source Raman spectrometer and near-infrared reflecting spectrometers are designed and integrated to analyze the rock samples. Furthermore, OpenCV library is used for the rock and water samples.